Section 6.3 exercises. Let's take a look at problem number 1. We're given that sine theta equals 4/5 and that theta lies in quadrant 2. I would stop right there and draw the picture first to illustrate that. So we have a quadrant 2 angle right there that takes us quadrant 2, and then we draw our acute right triangle right there. I'm going to translate the information to my triangle. Sine theta is opposite over hypotenuse. So the opposite here is 4 and the hypotenuse is 5. Now let me take a peek at what we're asked to find. Find the value of sine 2 theta, cosine 2 theta, and tangent 2 theta. So that means I'll need to get this length right here for x. So we'll use the Pythagorean theorem. 4 squared plus x squared equals hypotenuse squared. And if you recognize this to be a 3, 4, 5 standard right triangle, that would be really great. Otherwise, we do the arithmetic. 5 squared is 25, 4 squared is 16, so when we bring the 16 over, we get 9, and x is plus or minus the square root of 9, so plus or minus 3. We use x equals -3 since we are in a quadrant 2 position for our angle. Now let's take a look at the identities we need for sine 2 theta. Sine of double the angle is equal to 2 times the sine of the angle times the cosine of the angle. So using my right triangle, 2 times the sine of the angle, well, that's given to be 4/5. And the cosine of the angle, that's adjacent over hypotenuse, so that's -3/5. And performing the multiplication straight across the tops and the bottoms gives us a final value of -24 over 25, and that's the value of sine 2 theta. To get the value of cosine 2 theta, there are 3 identities for the cosine of a double angle. And any one of the 3 used will result in a same answer but a slightly different way to calculate it. I'll use that cosine 2 theta is equal to the square of the cosine minus the square of the sine. And we'll pull each of these values right off the triangle. So cosine 2 theta is equal to the value of the cosine of the angle, that we know is -3/5 squared, minus the sine of the angle, that's given to be 4/5 squared, and square each one individually. 9/25 minus 16/25, and then add that together, and we get -7 over 25. And that's the value of cosine of the double angle. The tangent, squeeze the identity in here. The tangent of 2 theta has only one identity form, and that is twice the tangent of the angle divided by 1 minus the square of the tangent of the angle. So we'll pull those values off the triangle, and then we'll have some arithmetic to do. 2 times the tangent, now the tangent's opposite over hypotenuse, so that'll be 4 divided by -3 divided by 1 minus the square of the tangent of the angle, and tangent of the angle is 4 divided by -3, and we have to square that. So performing the arithmetic in the numerator, we'll have -8 divided by 3, and in the bottom we have 1 minus 4 squared is 16, and -3 squared is 9. So that's -8/3 divided by, common denominator here, 9/9 minus 16/9 will give us -7/9. And then finally, taking the numerator divided by the reciprocal of the denominator will then give you a final value of 24 divided by 7. So it'll be -8/3 times 9 over -7. And that'll give us our final answer of 24/7. Let's take a look at problem number 2. Find the exact value of cosine squared 15 degrees minus sine squared 15 degrees. This is the right side of the identity, cosine square of angle minus sine square of angle, where the angle here must be the same. It is, and that's 15 degrees. So cosine square of 15 minus sine square of 15 is directly equal to the cosine of double the angle, and double 15 is 30. So we're working the identity from the right side as given, and we're expressing it in more compact form on the left side. Cosine of 30 degrees, I'm sure you all know by now, is square root of 3 divided by 2. Problem number 3. We have an identity to verify. Sine of 3 theta is equal to 3 sine theta minus 4 sine cubed theta. Okay, how do we approach this? A good idea would be to reduce the angles. We have multiple angles on the left and single angles on the right. So I'll have to rethink sine 3 theta as 2 theta plus theta. And then I'll use my identity for sine of the sum a plus b. And I'll write that out while I'm doing it. The sine of a plus b is the sine of the angle a, so that's the sine of 2 theta, times the cosine of the second angle, that's theta, plus the cosine of the first angle, that's 2 theta, times the sine of the second angle, and that is theta. So again, I'm using my identity for sine of a plus b and expanding that, where the a is substituted in 2 theta, and the b, we substitute the angle theta. Now, let's see. There's another identity for sine 2 theta, which we have up here at the top in problem number 1. So replace sine 2 theta with 2 sine theta cosine theta. So we now have 2 sine theta cosine theta times the cosine theta that's already there, plus cosine 2 theta. There's 3 identities to use there, and this sometimes takes some trial and error to know which one. We are moving completely towards sine function only. So I'm going to use the double angle identity for cosine that involves only the sine, and that is 1 minus 2 sine squared theta. And that's why I'm choosing that particular identity. The other ones involve cosine, and only this one involves only sine. So what do we have? We'll simplify a little. 2 sine theta times, this is cosine square. And in here we have a little distributions to do. So 1 times sine theta minus 2 times sine squared times sine will give us sine cubed theta. If you look at the right-hand side where we're going, it's starting to take shape. Now we have one problem of this cosine needs to be written in terms of sine, since our goal is to get everything in terms of sine. So I'm going to use the Pythagorean identity there and replace cosine square with 1 minus sine square. And we'll just write down the rest of it here so we don't lose it. Okay, now let's multiply this out. 2 sine theta times 1, and then minus 2 sine theta times minus sine square theta is minus 2 sine cubed theta. And write down the rest of my terms here. Now, everything is pulled apart. The like terms can be added together. And we have 2 sine theta plus another sine theta. That makes 3 of them. And we have negative 2 sine cubed and another negative 2 sine cubed. This is a 3, and this is a 3 from above. I miscopied that. And that makes 4 of the sine cubed thetas. And that's the right-hand side that we're asked to prove. Move on now to problem number 4. Use the power reduce identity to write an equivalent expression for sine of x to the 4th power. It does not contain trig functions of powers greater than 1. Okay. First, we'll make the following move, that sine to the 4th of x is equal to sine square of x quantity squared. And then we'll grab our power reduce identity. Sine square of x is 1 minus cosine of twice x all over 2. That's our power reduce identity for sine squared. We'll then substitute this right into here, and then we'll work out the square and see what results in that. So we'll have 1 minus cosine of 2x all divided by 2, and that needs to be squared. Squaring the top and the bottom, so carefully squaring the top, full expansion, this is in first, outside, inside, last. You get 1 minus 2 cosine 2x plus cosine square of 2x. Squaring the bottom gives us a 4. Now, we still have a trig function here with a power greater than 1, so we're going to need our power reduced identity for cosine square, and that is 1 plus cosine of 2x all divided by 2. These two power reduced identities are almost the same, but they differ in one is a minus and one is a plus. I'm going to pull this fraction apart by separating the numerators first, then I'll use the identity. So 1 over 4 minus 2 over 4 cosine 2x plus 1 over 4 cosine square 2x. Now I'll use the power reduced identity and replace cosine square of 2x with this. There's one little tricky spot here, reducing that fraction. Recopying over to here, put a bracket in there. Cosine square of angle is 1 plus cosine of twice the angle. So this expands to 1 plus cosine double the given angle, and the given angle is 2x. So doubling that gives you 4x. That's the little tricky spot you have to be aware of. Okay. Now, a little bit of arithmetic, and we'll be done. So we have 1/4 minus 1/2 cosine 2x plus, this is 1/2, and the 1/2 can be brought to the front as 1/8, leaving us with 1 plus cosine of 4x inside. Then I'll distribute the 1/8 through, and then we'll add up our like terms, and we'll be there. 1/8 times 1 is 1/8, and then 1/8 times cosine of 4x. Now add your like terms. 1/4 and 1/8, well, that's 2/8 and 1/8 is 3/8. And we have a negative half cosine 2x there. And we also have our 1/8 cosine of 4x there. And these angles cannot be simplified by adding in any way. And that is our final answer, and there's no more simplification to be done there. So what we've done is trade powers for multiple angles. Problem number 5. We're given the cosine of 210 degrees to be negative root 3 over 2, and we wish to use the half angle formula to find the exact value of cosine of 105 degrees. Okay. When you use the half angle formula, the given angle is theta, and the angle you wish to find is theta over 2. That's the half angle, because 105 is half of the given angle 210. So we'll use the formula here for half angle, for cosine. Cosine of theta over 2, and that is 105 degrees, right? Theta over 2 is 105 degrees. And that is equal to, it's either a plus or a minus in front of the square root. We'll determine that in a moment. The inside is 1 plus cosine of theta. Theta is the 210 degrees. And that's all divided by 2. Okay. Now, the angle that we wish to find, 105 degrees, this is in quadrant 2. And in quadrant 2, cosine is negative. So we will choose the negative in the formula for the half angle. Now we just work this out. Cosine of 105 degrees is minus the square root of 1 plus, what is cosine 210 that was given is negative root 3 over 2. And all of that is divided by 2. Okay. Continue to simplify that. negative in front of the square root. So we can find a common denominator there. This is 2 over 2 minus root 3 over 2 is 2 minus root 3 all over 2, and that's still divided by the 2 we have there. And then continue to simplify. Numerator divided by 2 is the same as numerator times 1/2. So we'll have under the square root 2 minus square root of 3, and that will now be divided by 4. And finally, we have a square root of a fraction. So what we'll do is take the square root of the top, and looks a little strange to have a square root with another one inside, but that's perfectly fine. You can push this into the calculator to get an approximate value. Square root of a fraction is the square root of the numerator, I just wrote that, divided by the square root of the denominator, and that's 2. And that's how we leave our final answer. And that's the conclusion of section 6.3 exercises.